You know when you see a rainbow shimmering on an oil slick or a soap bubble? Well, what you're seeing is the physics of light right there in action. But there's this even cooler, more mysterious version of that, first written down way back in 1666 by Isaac Newton himself. And they're these perfect, almost ghostly circles of light that we now call Newton's rings.
I mean, it really does look like magic, right? But the explanation is one of the most beautiful proofs we have that light isn't just a stream of particles, it's a wave. So let's follow the clues and see if we can crack this thing.
All right, here's our game plan to solve this mystery. First, we'll look at the phenomenon itself, the ghost in the glass. Then we'll check out the incredibly simple setup that makes it happen, this air-thin gap. After that, we dive into the physics of what happens when light waves collide. That's going to help us figure out the secret of the circles. And finally, we'll decode the pattern and see what it actually tells us about light itself.
Okay, let's start with what we're really looking at here. You've got these concentric rings, some bright, some dark, and they just appear, seemingly out of nowhere, just when you put two pieces of glass together in a very specific way.
So, the first thing you've got to understand is that these rings aren't actually in the glass. They're not etched in or anything. They're an optical effect, a kind of ghost created by light waves interfering with each other. And you see that central spot? The fact that it's dark is super weird, and it's actually our first major clue. So here's the twist. The effect isn't created by the glass, it's created by what's trapped between the pieces of glass. And the setup honestly couldn't be simpler.
That's it. That's the whole setup. A totally flat piece of glass, and then you put a special lens on top of it, one that's curved on one side and flat on the other. Where they meet, they touch. But as that lens curves away, it traps this microscopic wedge-shaped layer of air. And that razor-thin film of air, that's the entire stage for our light show.
And this air film, this is our main character. Its thickness is everything. Right in the middle, its thickness is basically zero, and as you move outwards, it gets progressively thicker. This gradual change is the absolute secret to the entire pattern.
Okay, now things get really interesting. When light hits this setup, it doesn't just pass straight through. Part of it splits off and takes two slightly different paths before it comes back to our eyes. And where those two paths recombine, that's where the magic happens. So, picture a single wave of light coming down from above. Some of it, let's call it ray 1, bounces right off the bottom of the lens. But the rest of the light, ray 2, keeps going. It crosses that tiny air gap and then it bounces off the top of the flat glass plate below. So now you've got these two reflected rays, both born from the exact same source, traveling back up together, ready to interfere with each other.
And here's where it gets really wild. Those two rays don't just add together. One of them actually gets flipped upside down. It's a fundamental rule of optics, and it changes absolutely everything.
Think about it like a wave on a rope. If you flick a rope that's tied to something loose, the wave just bounces back normally. But if it's tied to a solid wall, the wave reflects back, but it's inverted. It's upside down. Light does the exact same thing. Ray 1 bounces off air that's the rarer or looser medium, so no change. But ray 2 bounces off the solid glass plate, the denser medium, so it gets flipped a full 180 degrees. This little phase shift is the secret key to the whole puzzle.
So because of that one little flip, the rules for what makes a bright spot and what makes a dark spot get turned completely upside down. Normally, when two waves are perfectly in sync, they add up and you get a bright spot. But here, because one of them is already flipped, they totally cancel each other out. They make darkness.
And that flip logic finally solves our first big mystery. Why is the very center, where the glass is literally touching and the path difference is zero, why is it completely dark? Logically, it feels like it should be the brightest spot of all. Well, right at that center point, the air gap is zero, which means both light rays travel the exact same distance. So the only difference between them is that one of them got flipped upside down. And what happens when a normal wave meets a perfectly inverted wave? Yep, they create perfect cancellation. Darkness. Mystery solved.
Okay, so we've cracked the dark center and we get why there are alternating bright and dark fringes. But why are they perfect circles? Why not squares or wavy lines or something else?
The answer is actually really elegant. It's all in the perfect symmetry of our setup. It comes right back to that air film.
Here's why they're rings. For, say, the first bright ring to appear, the air gap needs to be a very specific thickness. So where else in the setup does that exact same thickness exist? Well, it exists in a perfect circle all the way around that central point where the glass touches. The collection of all the points that have the exact same thickness is a circle. That's why each fringe is a perfect circle. Simple as that. Now, what's really cool is how the pattern changes depending on the light you use. If you use a pure single-color light, like that yellow glow from a sodium lamp, you get these beautiful, sharp, distinct rings. But if you use white light, which has all the colors of the rainbow in it, you get this gorgeous chaos of colorful, smeared-out rings. That's because each color, with its own unique wavelength, creates its own set of rings, all slightly offset from each other.
Okay, so this is way more than just a pretty optical trick. Newton's rings are actually a powerful measurement tool. The pattern itself is hiding information inside it.
If you look really closely at the rings, you'll notice they're not evenly spaced. As you go out from the center, they get skinnier and more crowded. They get squished together. This is a direct clue from the shape of the lens. Because it's a curve, the air gap gets thicker faster the farther you go from the center. And that's the key to our final insight.
And this is the real payoff. It turns out there's a direct mathematical relationship between the size of any given ring and the wavelength of the light that's creating it. What that means is we can measure something we can easily see, the diameter of a ring, and use it to precisely calculate something we can't see at all, the actual wavelength of the light itself, right down to the manometer. How cool is that?
That's really the heart of it. We're decoding a hidden fundamental property of light just by analyzing this beautiful pattern it creates. The rings are like a visual readout of light's very nature as a wave. It's incredible.
It's just a powerful reminder, isn't it, that sometimes the biggest, most profound discoveries don't come from massive, complicated machines, but just from a new way of looking at something simple. It makes you wonder, what else are we missing? What else is hiding right there in